Take a look at two additional tests. We're going to look at the comparison of series. So I have the direct comparison test and the limit comparison test that can be used to test if things converge or diverge. If I'm looking at the direct comparison test, then for the convergent test, the terms of the series have to be pretty simplistic, and the series must have a couple of special characteristics in order for this test to be applied. So I need to know that for a direct comparison test that I can compare this to something else. Okay, so if I have 1 over 2 to the n, I know that's geometric and I know that it converges. I can compare 1 over 3 to the n to the same thing. If I look at number 2, I can say, oh, that's a p series, but this other one is not a p series, so the rule can't technically be applied there. Same thing with 3. It's easily integrated, but the other one is not easily integrated. So it's looking at pairs that have a similar partner, but not completely available. So if I say that I'm using this test, if B sub n converges and the sequence that I'm comparing it to is smaller, then A sub n has to also converge. If A sub n diverges and it's less than the other comparison, then that's also going to diverge. So what does this actually look like? If I'm looking at this, this is similar to 1 over 3 to the n. So think about like n behavior. I know that 1 over 3 to the n is a convergent geometric series. So if I compare the terms that I get, I can see that A sub n is in fact less than B sub n, which tells me that this also has to diverge. So it's looking at who can I compare this to, and then let me generate a few terms. And if the terms are less, then it also converges. The limit comparison test is another handy one. And if I'm looking at the limit comparison test, it typically is used when something resembles a p-series or a geometric series, but you can't get that term-by-term comparison you need for the direct comparison test. So in this test, I can show this a n plus b as a quotient here. Looks kind of like 1 over n, right? Kind of like 1 over n. I could compare it to 1 over n. If I take the limit and I divide it by the comparison of 1 over n, I get that it's 1 over a, which would be greater than 0, and I can conclude that it diverges. So you're dividing here the existing function by a comparison function and then taking the limit as n goes to infinity. If you get something greater than 0, then it's going to conclude that the given series diverges. If you get something less than 0, you can't say it converges. So it can only prove that something diverges here. So it's not helpful to make a final determination with convergence or divergence, but it is helpful if you want to rule out that something diverges.